There we go. All right, chapter 3, section 5, day 3, the last day of chapter 3 in general. Okay, so in chapter 3, section 5, we're dealing with this intercept form. This factored form is another way to describe it, to use the terminology from chapter 2. Sections 1 through 3, we were dealing with ax squared plus bx plus c, what would be called a standard form of a polynomial. This is the factored version of that. So if you recall back into chapter 2, when we factor something, we break it down into these parentheses, right, making it one string multiplication of these objects. This is useful for this section, for this topic being graphing quadratics, graphing these parabolas, these U shapes. It's useful because we're going to be able to pull out two x-intercepts from that information, from those parentheses. They'll end up being what we call zeros of the function. And that's a term that came up particularly in yesterday's lesson. A zero of a function, and this information you might want to throw down your margin if you haven't. Okay, a zero of a function refers to an x-intercept, or visually speaking, where it crosses the x-axis. They're called zeros because it's when y equals 0. You'll notice with both of these forms that the y value in the coordinate points are 0, meaning that it goes up or down 0 and it's locked on the x-axis, right? Making these x-intercepts, whatever they may be, right? Now, on day 1 of this lesson, we use that information to find those two coordinate points, those two x-intercepts, and use the midpoint formula between those two values to find out what split them in half, which would be the axis of symmetry. It's the axis of symmetry because on both sides of that U shape, it's going to be perfectly reflected. And it makes sense then that the axis of symmetry should split these points in half. And that was also important because that axis of symmetry will also help us identify where the vertex is located, because that x value for the axis of symmetry can be plugged back into the original equation, whatever that equation may be, and it will spit out the y value for that coordinate point, giving you the vertex. And so on day 1, when it came to graphing in intercept form, we're able to take the two x-intercepts, find their average, find their midpoint, find what splits those two x-intercepts in half, and use that to make the vertex. We now have our 3 critical points to graph a parabola, that U shape. On day 2, it was a little bit different. Day 2 focused on these two examples, and they both kind of had the same outcome, all right? And they both actually had kind of the same starting point. In both cases, you were given a quadratic function, but both of these should be familiar to stuff earlier in this chapter, in that these are polynomial sentences. Different than obviously what we're dealing with within this section where we have a factored form, these parentheses. A polynomial sentence is just going to have these terms added or subtracted with each other, right? And so this is what we typically saw in sections 1 through 3. This will also recall us back to what we did in chapter 2, where we dealt with these kinds of polynomials when we were asked to factor them. We started with the polynomial sentence, and in this case, we would use something like X method, or asking that riddle, finding greatest common factors, to basically break up this polynomial sentence into a pair of parentheses. Same thing goes for this one, in that we would also be factoring it. We would pull out our greatest common factor first, and then we would identify it as a difference of squares, which would again give us 2 parentheses multiplied by each other. And the reason why that's important is because then it puts it in intercept form. Why would that matter based on how these were written? In this case, it said to literally write it in intercept form, which is just a fancy way of saying factor the given polynomial, right? And identifying the vertex was the same strategy that we used before, split it in half with that axis of symmetry, and then use that value to plug it back into the equation to find out what your y value is for your vertex. But in this one, it was a little more subtle how it was worded. It says find the zeros of the function. Again, I said it before, and it's worth putting down the margin if you haven't already. The 0 refers to an x-intercept, where it crosses the x-axis, and that only happens at x-intercepts, right? And that means that having it in intercept form is a quick way to identify where those locations are. And so when it says find the zeros of the function, it's useful to rework this, rearrange this into the intercept form so that you can quickly identify what those zeros are. For instance, in this example here, the zeros would have been -1 and +5. Again, taking the opposite of both those signs, right? So that is useful in that problem. For today we're going to now talk about a different kind of family of problems, different kind of family of questions. And this is where I'm going to refer you back to what we talked about in chapter 1. In chapter 1, when we deal with algebra type problems, and this falls under the umbrella of algebra, one of the families of questions had to do with, all right, now instead of being asked to graph something or solve something, now you're going to be asked to basically create an equation, to define an equation given some information. Now, in chapter 1, we dealt with like, all right, here's a visual graph. Based on this visual graph, identify the equation of whatever it is that's happening, right? That's a typical way that's been asked. You've definitely come across that before with linear functions. In this one, you're now going to be given different kinds of pieces of information, coordinate points, essentially, right? And I'm going to go through both of these as far as like, based on the type of information that we're given, how can I use that to create an equation? Because in this question, it's saying to write a quadratic function. Now we know 3 different forms of a quadratic function. I'll talk through each of those in a second, but they ask us to use the standard form. And again, I'll identify what that is and how we can rearrange it to meet those requirements. Okay. But one thing I want to point out is that it does not ask us to graph these results. Our job here is not to create something visual, which is ironic because the entire name of this unit has to do with graphing. Instead, what we're asked to do in this question is to literally write a formula, an equation. All right, so let's jump to the whiteboard and get started with that. All right, so before I jump into that example, I want to identify the 3 different forms of a quadratic function that we have now covered. All right, 3 different forms. Form number 1, the one that we dealt with in the first 3 sections of this chapter. Standard form. Standard form, or another way to think of it is, this is the polynomial sentence, right? Polynomial sentence. Standard form is going to take on this look. ax squared plus bx plus c. This is the kind of thing that we saw in chapter 2 for the first several chapters, where we had a polynomial sentence and we would collect like terms, so on and so forth. And this is also what we attacked for the first 3 sections of this chapter. In section 1, it was just the ax squared, where we learned what a did to the shape of a parabola, the u shape. And then in section 2, we added in this factor of plus c, right? And so we learned that c moved that u shape, that parabola, either up or down, depending on what the value was. And then in section 3, we added in this last element, the bx. And we learned that using that special mini formula, negative b over 2a, based on these coefficients, we'd be able to identify the axis of symmetry and in turn the vertex of whatever this may be based on those values. Okay, but standard form, just on appearances, right, is going to have this kind of polynomial sentence type of look. It's still going to produce the same type of shape of a graph, but in the sentence form, that's what it's talking about. So for this question, this first, the example we're going to be doing today, when it says to write it in standard form, they're expecting this kind of result. All right, so form number 2 that we covered. This was what we covered in section 4 of this chapter, was vertex form. Now, vertex form involved a slightly different look, obviously with this parentheses now, right, and different letters. But in vertex form, we now have a parentheses, which technically is a factored version in some way, shape, or form of the original. But specifically, it was a parentheses that was raised to the power of 2. This is going to represent that vertex form. Vertex form will only have this kind of look. And what we learned in vertex form was that this was one of the most convenient forms of a quadratic, similar to like with linear functions, how y equals mx plus b is one of the most common forms that we use for a line, because there's so much useful information we could just pull out from looking at the equation. In vertex form, this HK combination told us exactly where the most important point of a parabola is located, the vertex. That's why it's called vertex form. No real surprise there. The careful thing we just had to be aware of here in section 4 was that I would take the opposite sign of whatever was inside the parentheses, kind of like what we do for the zeros in intercept form. And I keep the same sign of whatever's out here. And that would end up giving me my X, Y coordinate combination for whatever my vertex was, right? And so that was a very valuable, very quick way to graph something on the coordinate grid when it came to graphing a quadratic, right? Now, form number 3 is what we're talking about in this section, section 5, called intercept form. Now, intercept form, or another way you could describe it is as factored form, also starts with the same letter A, but now we have these different letters. And again, the types of letters that they have actually are not all that important. The fact that we use P's, Q's, H's, K's, B's, C's, they're just going to represent numbers that will be there in the place of them, right? So in intercept form, we're going to see these parentheses again, similar to what we saw in vertex form. But obviously, this is a very different look than the vertex form, because in this vertex form, I had a parentheses squared, meaning that it's that x minus h, whatever h is, times itself. In this intercept form, I have 2 different combinations of parentheses. So fundamentally different than vertex form, right? And also there's no value out here. Now, one thing I want to emphasize, we have talked about these 3 different forms now. Technically, I can rearrange any one of these to look like one or the other. It would take some work, more in some cases than in others, but particularly with these 2 forms, vertex and intercept, if I were to use my techniques from chapter 2, namely taking this parentheses and squaring it, so taking x minus h and multiplying it by itself, and then collecting my like terms throughout this function, I'm going to get back to this kind of form. Same thing here, right? Where I would take this parentheses and using distribution and collection like terms, multiplying it with this parentheses, and then multiplying through that A, I'll get back to this form as well. So standard form, the reason it's called that is because this is the most fundamental way to write a function, an equation in general. These happen to be very convenient rearrangements of the same thing. So it is possible in a lot of cases to take whatever standard form I have and rearrange it to look like vertex form, or to rearrange that to look like intercept form, right? So these 2 are really just rearrangements of the standard form. And that's really what we're going to get into in today's lesson. So these are the 3 we've covered. Let's start applying. All right, so for our first example, we're going to be given some information, some coordinate points. And we're going to be asked to create a quadratic function based on that information. So our first example for today, part A, we're given this information. We're told that the vertex of some quadratic, some U-shape, some parabola is the following coordinate point. We're told that the vertex is at -3, 4. And that's all we're given. We're just given a single coordinate point, and we're asked to write a quadratic equation that will contain that point. Now, it has to be the vertex, right? So for the record, there are actually an infinite number of parabolas that have a vertex at this point, and I'll talk about that in just a second. But the trick here is going to be, based on the information I'm given, how do I write it in one of those 3 forms? Okay. Now, it is possible to write it in any one of those 3 forms, but some are going to be more convenient than others. Based on this information, and actually more specifically, based on this word, it should be pretty obvious which of the 3 forms I should use. Vertex form. So if I'm going to use vertex form, namely a times x minus h squared plus k, if I'm going to use this vertex form, I have to be able to interpret how this information goes into this form, right? So in this case, if I'm going to be putting these values in here, I just have to be able to identify where they're going to go. So this is an x, y value of a coordinate, but I also need to know within this form what pieces are the vertex, namely h and k. H is going to represent this x value, k is going to represent that y value. And so really all I'm doing at this point is I'm just substituting in the stuff I know and leaving the other stuff I don't know as is. So A is still going to be A. It's still going to be X minus. I'm going to replace H in just a second. And then I have plus K. But now I'm going to substitute. This is going to be H in my vertex form. So that -3, and you're going to see why I threw in that minus sign to begin with. This is ultimately why I end up flipping the sign when I start with the vertex form or whatever. Okay, this is why I end up flipping the sign, because see how it's X minus in the original form? So that when I'm subtracting H, well, H in this case is a -3. So when I subtract the negative, you should understand that this is going to turn into a plus. Right? And I take the time to write it out because that's one of the more common mistakes. People are like, oh, it's a minus already, so I can just put in -3. No, technically it is a minus -3 because the -3 is the actual H value. Now, K is a +4. So when I add a +4, it's just +4. Right? No real special thing happening there. And so simplifying this, and really by simplifying, I mean like changing that to a plus, I'm going to end up with this in vertex form. Let me write this in 2 different colors. Now again, this being the opposite sign in my actual vertex, but here is my vertex form based on that information. So real quick, one thing I want to point out, we don't know what A is. Now you will be given some problems where it's going to be asking you to actually figure out what A is going to be worth. And the way you would do that is you would require another coordinate point. So it might say like the vertex is this, and then it also contains this other coordinate point. And if it contains that other coordinate point, you're literally plugging in that XY value for that coordinate point in for the X, and then the Y is going to represent whatever the function equals. Because technically all along this way, Y equals these values, right? Y being whatever coordinate point is going to pop out when I plug in some random X value. So if they did give me some other coordinate point, I could plug it in, X being that first value, Y being that second, and I'd be able to rearrange this formula to solve for A. Okay. Now in this case, we are not given that. We're not given another coordinate point, so technically A will stay A. But what big ideas will have you do is just ignore A altogether. So if I ignore A altogether, this is going to be my vertex form based on that information. The fact that there would be an A there just represents the fact that there are lots of different kinds of narrow or wide parabolas that will contain this vertex, right? But one thing to also point out, in this question, in this problem, we are asked to write this in standard form. This is not standard form. So in order to write this in standard form, I need to do what we did in chapter 2. Namely, I need to distribute and collect like terms. In other words, I need to take this parentheses, square it, then add in the 4 after the fact, and I'm going to end up with a polynomial sentence, that ax squared plus bx plus c. All right, well, if I take this x plus 3 and multiply it by itself, I'm going to end up with x plus 3 times x plus 3. That's where that squared technically comes from. That's the same thing as this. And then don't forget that I also have this plus 4 on the outside. All right, so for the record, this is still the same exact version of this. We rewrite it in this squared form to show where the vertex is actually located. But I can rewrite it this way, and this is useful particularly if I'm going to be distributing and multiplying just like we did in chapter 2. So now doing this part, I'm not going to go into as much detail as I did in chapter 2 because we've technically already done this, but in order to do this polynomial multiplication, I'm going to start with this first object and multiply it throughout this parentheses. So I would get x times x, or x squared. I would get x times positive 3, giving me positive 3x. Then I'd be done with this x, and I'd move on to this positive 3. That positive 3 times throughout this parentheses. I would end up with x times that 3, 3 times that x. Combining them, I would get plus 6x. And then lastly, that positive 3 times that positive 3 would give me plus 9. So I skipped the combination of like terms, mostly because we covered that in chapter 2. But if you need explanation where that comes from, you can talk to me after the lesson. And again, don't forget about the +4 at the back end. So now I technically can combine these two like terms, the +9 and the +4. +9 and +4 is going to give me +13. And there is my standard form of that vertex form of equation. Right? Technically, that's an A, B, C, ax squared plus bx plus c type of form. This is a standard form, all based on the information of the given vertex. All right, let's do one more. This one I'm going to give you intercept form, or information that's useful for intercept form. Okay. Let's go ahead and jump right in. So in our second example, I'm going to give you a little bit less information than what's actually in the problem, just to simplify things. But here we're given these two coordinate points, right? So it'll say either contains, or like in this case, it passes through. What passes through? Whatever the parabola is on the coordinate grid is going to pass through the given points, or contain the given points, right? And here are the points that we're given. -9, 0, and -2, 0. So they give us two coordinate points here, right? So based on these two coordinate points, my job is to write a quadratic equation. But there's something very important to notice about these values. These are going to end up being x-intercepts. Why do I know that? Why do I know these are going to be x-intercepts? Because of this right here. Because these y values are 0. When my y values are 0, that literally means that if I were to graph this point, I would go left 9, up and down 0. This one would be left 2, up and down 0. That up and down 0 value means literally I'm locked into the x-axis, therefore making it an x-intercept. And that's a very important fact, that these are x-intercepts, because I have a form for that for a quadratic equation. Because ultimately, based on my information, I want to be able to plug it into one of those forms, right? In the last problem, we were given a vertex, so vertex form was handy. In this case, x-intercepts are given, so intercept form is going to come in handy. So intercept form tells us this. That's going to be a times x minus p, and then x minus q. Right? Now, p and q are going to represent where those intercepts are located. So this -9 and -2 are going to end up being p and q. And it doesn't matter which one's which. The order of these parentheses actually does not matter, as with all multiplication. So when I plug these values in, let's go ahead and see what happens, right? So when I plug in -9 and -2, again, my suggestion is to leave in the structure, in other words, this minus sign and that minus sign, and then plug your values in. So my x-intercepts were -9 and -2. Now, for the record, these were also what we would call my zeros. In other words, the value on the x-axis that is where it crosses, right? So -9 and -2 are my zeros, or my x-intercepts. Now, in intercept form, I have to make sure I go into the structure, and because it's a minus sign, it's going to end up flipping this to a plus, okay? Now, had them in positive values, then it would just simply be x minus that value, but I do have to bear in mind that negatives will play an effect. So that when I rewrite this, okay, I'm going to have the given results. So minus a -9 is going to turn into +9, minus a -2 is going to turn into a +2. So there is my intercept form based on those x-intercepts I was given. Now notice again, they didn't give us any other coordinate points. So A in this case on big ideas is just going to be 1, right? The fact that it disappears doesn't mean it goes to 0. It's just they're going to imagine that there's a 1 there. Again, there are lots of different parabolas that will contain these 2 points. That A represents how you can have a lot narrower parabolas that contain these 2 points, or a lot wider parabolas that contain these 2 points. A lot of factors go into that. But for this, again, they want it in standard form. So similar to the last problem, that means I need to distribute, collect like terms. Let me do that really quickly. So again, technically my equation is y equals this intercept form. So when I distribute this, I'm going to take this x and multiply it through that parentheses. Then I'm going to move on to that positive 9 and multiply it through that parentheses. Collect my like terms and I'm done. So I'll make this a one-step problem. I'm going to take the x, multiply it through. X times x gives me x squared. X times the positive 2 is going to give me positive 2x. Hang on to that in your head. Because when I do this positive 9 now times x, that's positive 9x. Those two objects can combine to make 11x. And wrapping it up, the positive 9 times positive 2 is going to give me a positive 18. There is my standard form based on those y-intercepts. Forgive me, x-intercepts. Right. And one thing I want to point out here is that if I were to take this standard form, this ax squared plus bx plus c form of the quadratic, if I were to factor this, okay, using that riddle, what two values multiply to make 18 that also add to make 11? 9 and 2 multiply to make 18 that also add to make 11. I'd be able to factor it into this, right? Those are my factored forms. So this factored form would now be my intercept form for that quadratic. So I'd be able to identify the zeros, the x-intercepts, right? And I could back that up to here to identify what those specific zero values are, right? Back to even where I started in the problem. Again, all of math should be, not all of math, but all of algebra at least should be reversible, meaning that given my result I got at the bottom, I should be able to back up to where I began and vice versa. Anyway, that's what you'll be covering in this section. I'll go ahead and stop recording.